and welcome to week 5 of our lessons on Apex. This week we're doing 9.3.1, the study for entropy. Last week we were doing enthalpy, but this week it's entropy. Similar but different, all the same. So it's kind of neat if you're looking at a crash test in a car commercial. Typically in this first image has it what we normally would see is the car running into the wall and then crashing, kind of seeing that. The other image that they'll show you, and it'll play, is kind of that this is not the typical way. We don't see things going back to this very non-broken way. You don't see the reverse. Okay, so this whole idea of entropy kind of deals with this. So it's a measure of randomness. Okay, so after the crash, the wall and the car each have more entropy than they did before the crash. Okay, before the car crash, it was a very nice wall. It was clean. The car was kind of nicely not broken, and there was a pattern to it. But the more organized something, the less entropy it has. So the more chaotic it is, and random it is, so that crash, all the things are flying, the more entropy it has. Okay, so it's just kind of randomness that's going on. That's what we're looking at. So, in a simple kind of understanding, kind of check, is that, okay, image 1 has a pile of folded clothes. The pile, image 2 is that kind of pile's crazy, everything's in there. So which image shows the shirt with more entropy? And remember, the more entropy you had, the more crazy it is, or the chaos and spread out it is. So of course, B, image 2, has more entropy, okay? They're more randomly arranged. There's no definitive way that they are arranged. Okay, so we kind of move along this, and watching this is a very helpful video with this, and so with probability, and the deck of cards, my internet's going to be a little slow in buffering that, but it's a neat idea. If you have this deck of cards, and it's arranged, shuffled one way, if you throw it up in the air, what's the chances that it's ever going to go back to the same way it was before? It's not. It's, more likely to be in a random state. Okay, so this kind of happens everywhere in other places in the world, that a random configuration is more likely than an ordered one. Okay, stuff likes to be more randomly than being forced into an order. Okay, and so we're kind of, whether this also deals with spontaneity or spontaneous, meaning is it going to happen on its own? And what is more likely to happen. And this kind of relates to chemistry and with reactions. Are reactions more likely to happen on their own? Are they, it's a very much kind of what's going on with that. Now, we can kind of give a value to this, and increasing and not. So we have a second law of thermodynamics, and it's a law in science, so not like a theory, it's a proven law that states that the entropy of a system tends to increase. So that means it is more likely to become, more disorganized or more chaotic or more random. Okay. And what it also kind of means, and I like this reference, that the shirts scattered around the bed are not likely to rearrange themselves in a neat pile. Instead, they're just more likely to be more scattered into even more chaos. You're not going to they're not going to come together into a pile. They're more likely to be thrown around your room or whatever it is. Okay, so it just, overall, entropy tends to increase over time. Okay, so we can kind of make this what's going on. So we can kind of apply it to the entropy of the whole universe kind of increases. Okay, so because if random bits of dirt, sunlight, and water become organized, does that mean that it isn't true? So all these random seeds and dirt and stuff are coming together to make this plant. Okay, and I think this plays in there a little bit. Well, that's not what's supposed to happen, right? We just said that everything tends to become, disorderly. Well, according to the second law, it's just the plant can become more organized and the entropy can decrease as long as the whole universe is still increasing. So it's kind of like looking at the entropy of the sun, dirt, and water overall is increasing as they give energy to the plant. So it's not just that the plant can make that structure and grow up into the little, leafy plant or flower. That is getting more organized, but it's the overall universe is increasing the entropy. So, and it's a little confusing along with that, but go with it. Okay. This also deals with pretty easily looking at our, states of matter. So we have solid, liquid, and gas. And just looking at it, you can see which one has the atoms more randomly arranged. Kind of a little bit easy. They're spread out. They're, bumping the sides, doing whatever they need to do. That's gas. Okay. So they have the most entropy. Okay. And along with this, matter is most random in the gas phase. And we talk about the motion. Okay. Remember, as solid ice is shown in the image, they are locked into place. They vibrate. Then water, they can kind of move a little bit, roll over there and slide past each other. And then you get to gas and they're just bumping around like crazy. They're flying around in a quick, large area and have little attraction to each other. Okay. So as they start moving, they're definitely having more entropy as they kind of go on. Okay. And then this all relates to what we were learning last week with enthalpy, but that entropy and enthalpy are both part of what determines whether or not it happens. Okay? Because atoms are more randomly arranged in a gas than a solid, they have more entropy. Okay? But how can anything exist as a solid, right? If entropy is tending to increase, why would anything exist as a solid? Because everything wants to become, crazy like a gas and running around. And you kind of need both energy-wise and the exothermic stuff we were doing last week and currently this week to kind of help you along whether or not this actually happens. And next for the part 2, I'll kind of get into more that not all solids are the same. If you're looking at this, you have what we call crystal structures that are very repetitive throughout. Or then you can have also, solids like glass don't really have this repeating structural. We call them amorphous solids, and they have more entropy because they're more randomly arranged. Like this right here is like, purple, green, and it's very definitive. So we can look at that. This is an organized side and a solid. This one's more of random. It's kind of, I know there's like every other one. You see like the blue, red, but it's just kind of not held together. So which one has more entropy? B. Okay, so as you start to head through this a little bit, we're going to start talking about temperature, and the closer it gets to that 0 where stuff doesn't move, absolute 0 where we cannot get really anything is less than a lab, like all the way there too. It's a perfect crystal, and it's as organized as possible, but they vibrate like pretty much nothing, like a solid like molecule. That would have like almost like a very minimal entropy. But we don't have that. You would think that salt, which has, Na, which are seen as the purple ones, the Cl seen as the green ions, should look like it should have like perfect crystal. But in real life, you do have imperfections and different things going on. I'll preview for the next slide before I stop. I think I'll stop here and kind of show you what happens as we're dissolving stuff in water and going on with that, so that I don't want to, make this one too long and the other one too short. But anyway, hope you're having a good week.